work. I think we're good. Welcome to section 6. So our game plan for today is we're going to talk about these reaction families of the SN2, the E2, and then SN1, E1. And then we're going to end off with about 20 minutes on that mixed kind of practice between them. The real challenge of this lecture is not the mechanisms. The mechanisms for this lecture are really easy. They're these like 1 or 2 step mechanisms. The hard part is all of these reactions occur with the same kinds of reagents. And the hard part is determining which of these reactions is going to happen. So we will be talking about that, and that will be this kind of last thing of the GFP system. But first, let's make sure that we're all kind of on the same page about these types of reactions. Are there any logistical questions before we jump into things? Something weird is happening where it keeps making the noise like, I'm connecting, which makes me think like, do I have like a loose wire or something? Maybe. But let's jump in with SN2. So the broad idea behind this reaction is we are substituting some leaving group for a nucleophile, another kind of chemical group here. The arrows for this mechanism are referred to as a backside attack, and it's because the nucleophile is coming and attacking this antibonding orbital here, and then that breaks the bond. So it's a one-step reaction, which is nice and easy. But one thing that's kind of confusing is we call it SN2, but it's only one step. It's SN2 because of its rate law. So if you remember from Gen Chem, the rate of a reaction depends on the order of a reaction depends on how many types of molecules affect the rate. So here, the concentration of the nucleophile and the concentration of the alkyl halide affect the rate of this reaction. And so it's second order. The N in SN2 just is for nucleophilic, which means it's driven by a nucleophile. So, mechanisms, easy part. Hard part with SN2 has to do with 1, stereochemistry and getting the correct product, and then 2, figuring out when SN2 is a viable reaction to take place. So let's start off with stereochemistry. So the first phrase that should come to mind when you think about SN2 on the exam and the problem set is inversion of stereochemistry. So I know it's unhinged. Can we do our little call and response? Where I say SN2 and you say inversion of stereochemistry. Okay. SN2.
Inversion of stereochemistry.
SN2. Work with a little attitude. Yeah. So let's say what that means. When we do our backside attack here, we go through this transition state where we are starting to form this bond with the nucleophile, and we are starting to break this bond with the leaving group. And when our nucleophile adds, it's on the opposite side. So when we trace like the priority and assign RNS for these, if we assign RNS 1, 2, 3 here, it's clockwise, so it's R. And then here, if we do 1, 2, 3, it's counterclockwise, it's S. So we have inverted the stereochemistry. We've gone from R to S. If we started off with S, we would wind up with R. Now, this will happen 99% of the time. And we have never tested you on the 1% before, and I don't think that we will. But do you remember that weird problem set question that was like, I'm trying to make this ester, and I want the R version, but I wound up with the S one. What happened? And it was kind of a silly, goofy question. The kind of big premise of that question, or the thing that we wanted you to get at, was the reaction changed the priorities of things, and you had to renumber it. And so there is a case where that could happen here, and it would not switch. It would be R both times or S both times. Truly, we've never asked that question, and I don't think we will. So if you want to just be like SN2 inversion of stereochemistry, that's the golden way forward, I guess. Let's start off with some practice. So the practice, the first one's really easy. It's just writing a straight up mechanism. Second one is predicting the product with the correct stereochemistry. And there are a couple ways that you can draw that product. And so we'll talk about both ways that we can draw the product with the correct stereochemistry. And then the last one, we've given you a product. You have to identify what reagent here was the nucleophile, and then draw a starting material molecule that has the correct stereochemistry. And these are on pages 3, 4, and 9 of the problem set. So I'm gonna give you like 2 or 3 minutes to try these out. And I'm gonna unplug in this iPad thing. Okay, so let's work through these. So the first one, we have the sodium on there, and we know that sodium is just a counter ion hiding a negative charge. So OH minus is going to go and do the backside attack. Bada bing, bada bang, we're done. Why do we not have to worry about stereochemistry on this molecule? Yeah, it's not a stereocenter, so we don't have to worry about inversion of stereochemistry. But over here, we take off the sodium. We have the S minus. We do our backside attack. We do have to worry about stereochemistry this time. So there are 2 main ways of drawing the product, and it's the same product, it's just 2 ways of drawing. So the first one, we are going to draw it with the iodine coming from behind, with the thiolate coming from behind and adding at this point right here. And so we would have the SCH3 added in the plane, and then our wedge and dash would just kind of shift down. So both of them stay as wedge and dash, but they have shifted to the side. It's kind of like when we initially add it, it would be like right here, but then it's going to adjust and equilibrate to the sp3 hybridization. That's option 1. Option 2 is we are going to put the SCH3 exactly where the leaving group was, so SCH3 here, and then we are going to swap the wedge and dash. So we are going to put the hydrogen on a wedge and the methyl on a dash. And when we do that, that also inverts the stereochemistry. The way to kind of convince yourself that these 2 methods are equal is assign R and S. So initially this compound is R, and then both of these over here are S. And I will let you check that on your own. But that's how we did the inversion of stereochemistry. Okay, for the bottom one, Which of these things look like they could have been a nucleophile that attacked? The CN. And so that would be CN minus, but when we write CN minus as a reagent, we typically put an Na on there, because we're never just going to have a charged thing on its own. It's always going to be balanced with that counterion. Okay, so we need to draw what the starting material was with the inverted stereochemistry before this reaction happens. And the way that we can do that is, again, the two options, either one. So I'm going to do the just swap the wedge and dash because I think it's easier. So I'm going to put, I could put iodine or bromine, whatever your favorite halogen is, go for it. Then you would have your methyl, and then you would have your hydrogen. The other way that you could draw it is with the bromine here, and then your methyl and your hydrogen staying as they were. Okay. Any questions on these? Yeah, I'll start. Yeah, it could be chlorine or iodine. Usually not fluorine, but could be potentially. So I figured out it's the charger, but it keeps doing it, and I'm like, this will die, and I won't be able to use my iPad to teach if it does not settle down. So I'm keeping an eye out for her. Cool. Questions on her? The rest, this whole column over here, it's really mostly reference info, but I want to touch on a few things. So when we're deciding whether or not reagents are good candidates for SN2 reactions, there are three main factors that you talked about a lot in lecture. The most important one is sterics. That one is going to be more important than all of the others. So steric hindrance is just the slowing down of a reaction due to bulky parts of the molecule. It has to do with electron repulsion. But think about it this way. When the nucleophile is trying to do a backside attack, if we have fewer things kind of blocking that backside carbon, then it's going to be really easy to do SN2. Whereas over here, if the nucleophile is trying to do a backside attack on a tertiary carbon, remember each of these are methyl groups that have their own hydrogens, each of them all having electron clouds around it. And so it's going to be very hard to do SN2 for tertiary. In fact, it fully just won't happen. So this is the big determination factor of whether or not we do an SN2. We also have leaving group ability, which is just how likely is this thing to leave and be kicked off, which we have a way of ranking with pKa values of conjugate acids. One I'll point out here is this tosylate, which we abbreviate OTS, and it has this structure. The reason I'm pointing it out is because she will come back in lecture 7 tomorrow. So you're going to learn another reaction with the tosyl group. Nucleophilicity, knowing that cyanide and this thiolate are really good nucleophiles, and then bad nucleophiles are something neutral like water. Typically a good nucleophile has to have a buildup of charge somehow, so we don't want it to be neutral. Now, this list is for the polar protic solvents. Do you remember we talked about the solvent effects for a page in lecture? Some classes test a lot on solvent effects, and there's a lot that you can do with that. Some classes also test a lot with temperature effects with these reactions. We do not. So I think you will find 0 problems in the homework that have anything to do with solvent, and you will find 1 problem on 1 practice test that has to do with the solvent. If there is solvent stuff on the exam 2, I will make a note of it in the exam 2 review. So if you want to just not worry about solvents, that's fine. If you want to learn that page and learn the kind of basic facts that we said about it, that is also fine. But I'm not going to emphasize it as heavily since we don't test it as much. One kind of notable key figure that you are going to see in this lecture and the next lecture is tert butoxide. So it's this tert butyl group with an O minus. My favorite alias of tert butoxide is Kotbu, K-O-T-B-U, Kotbu. And this is a notable figure because it reacts in a very specific way that is not super common. So this thing is an OR minus, which if we look at our nucleophile chart, OR minus we would think is a pretty good nucleophile. But this tert butyl group is super bulky. And so because of that, if you have tert butoxide, this is not really going to do the SN2 attacks Because even though it has that O with a minus charge, this is so bulky that it's going to make it hard to do that attack. So we say it's a poor nucleophile. But, it is still a strong base. And this poor nucleophile strong base combination is pretty rare. Like, this is one of the only ones in this class that we will teach you about that is a poor nucleophile but still a strong base. And I don't want to get too much in the details of this, but this has to do with this kind of deeper idea that being a nucleophile is a kind of kinetic term. So it depends on the speed of a reaction. And here, this is going to slow down the speed of the reaction, so it's not going to be as good of a nucleophile. Whereas base strength, do you remember doing stuff with like Ka and Keq, and you were able to calculate like the delta G, Gibbs free energy, from Gen Chem things, vaguely? You can do that because this is a thermodynamic measure. It's about stability of molecules, and so it's still a good base, even though it's bulky. So I kind of characterize this molecule as it has kind of the energy of Big du crime, where it's like mostly in line with all the other reagents, but it's also like a little like, I'm gonna mix it up. I'm gonna not do SN2. And so that's how I kind of refer to it, or kind of classify it in my mind, because otherwise it's just a boring molecule. Cool. Any SN2 questions before we move on? This is the point where I feel like we need the like Hannah Montana transition music, the doo-doo-doo-doo, like some transition sound. And so I'm accepting requests. If you come up with a sound that you think should be the pivot between topics and section, let me know, and I will try incorporating it. Because I do have my like little soundboard. Like I still have my for Texas Carbons. But cool. On to E2. So our big idea here for an E2 reaction is E2, we are eliminating our leaving group. We're not just substituting it. And when we eliminate the leaving group, we create an alkene. That's the big ideas here. So one kind of nomenclature thing that's a little tricky is, do you remember how when we talked about an imine, we talked about this being an alpha position, this being a beta position? So when we have an alkyl halide, we call the carbon that's connected to the bromine the alpha, and we call the one away a beta. So they've kind of shifted. Like over here with the imine, it's one away from the carbon and the CN double bond, and here it's one away from the bromine. But it's a kind of important distinction because we're going to be talking about beta hydrogens here, and you need to know where that is. So the way that this mechanism works is you have some molecule acting as a base, which I've generalized by just writing a B here. That is going to deprotonate one of these alpha beta hydrogens. So we are going to deprotonate that here. The electrons that are in this sigma CH bond are going to fold down, make an alkene, and then you kick off a leaving group. And so 3 arrows, 1 step reaction. Again, the E2, the 2 comes from the rate. So the rate depends on your concentration of the base and of the alkyl halide. And you wind up with an alkene at the end. You also have kicked off the leaving group and you protonated your base, but we care less about those. So just like we had our kind of call and response of SN2, it was 10 minutes ago. We're going to try that again. Look at your notes, take a second, regroup, and we're going to try that one more time. Whoa. So just like we had our call and response of SN2, thank you. We have a similar kind of stereochemistry concern that we have to take into place when we talk about the E2 reaction. And it is this anti-periplanar geometry. So let's explain it first, and then we'll do our call and response. So here, if you have your leaving group here, and you have your beta hydrogen, then the requirement here is you want the electrons in this sigma CH bond to be really close to this anti-bonding orbital between the carbon and the leaving group. So this is the first type of reaction that you've seen that has this kind of 3D alignment requirement, And if you go into take Chem 27, you'll see this is actually really common in a lot of biochem reactions. Like enzymes typically are going to hold substrates in a very specific position so that these kind of overlaps are possible. But basically, the reason that it does this is because when the base deprotonates the hydrogen, when you have these lined up just the right way, it makes this really easy to slide over into the antibonding orbital and break the bond. So when we draw our actual like curved arrow mechanism, we will draw it here, but the electrons are really kind of spreading out between the two atoms. And like this is going to form a double bond in the product. So this is the kind of essential alignment between the sigma CH, sigma star carbon leaving group. But why do we call it antiperiplanar? Well, if we did our Newman projection here, we would see our leaving group going up, our hydrogen going down. So they are in an anti-conformation for the Newman projection. And then these four atoms of the hydrogen leaving group and the two carbons that make the double bond, they are all in the same plane. And the plane that they're in here is the plane of the page. Like they're all like on lines, not dashes or wedges. And so we would say these atoms are periplanar. So putting it together, we get antiperiplanar. So the big thing that you should think of when you hear E2 is antiperiplanar geometry. So can we try our little thing? Pavlovian conditioning. So E2, antiperiplanar geometry. E2! Oh my gosh! That was not the same energy. So let's try again. Let's do like fear, like E2! Ah! Good, good. You know, lots of emotional states will pop up on problem sets and exams, so you need to be prepared with this fact and all of those emotional states. Cool. Any questions about what that means with antiperiplanar geometry and how we kind of got to it or why it's significant? Cool. Okay, so factors affecting the reactivity for E2. First off is that antiperiplanar geometry, and that's just kind of like a reality check of like, do we have beta hydrogens? Can they be antiperiplanar? And so here's an example of something where, do we have any beta hydrogens? This is alpha, this is beta. At the beta position, there are no hydrogens in there, just other like methyls. And so we can't do E2 here because we just don't have the beta hydrogens. So that's kind of like our reality check step. But then after that, if it's possible to do an E2 reaction, then our big determinator, our big determinant of whether or not we would do E2 is base strength. So this is the chart that we asked you to memorize in lecture 2, and I've just kind of color-coded it now to represent green, good for good bases. The orange are fair bases, and then the yellow ones are poor bases. And so basically our kind of boundary points are OH and better is good, H2O and worse is poor. And so it just kind of helps us divide this up into more of a like classification system that we're going to use when we do them all together. I will also at this point kind of point out this common mistake that I see students make is not recognizing the difference between alcohols and alkoxides. So ethanol, ETOH, it's neutral. It is an alcohol. And alcohols are both poor nucleophiles and weak bases. Like this alcohol, I wouldn't even typically call it a base. It's more of a weak acid. It's kind of weak everything. It's like water, basically. So that is an alcohol. But if we have NaOH, that is charged. And when we have that buildup of charge and a negative charge here, that elevates it from being a poor nucleophile to a great nucleophile. It elevates it from being a weak base to a strong base. And so the exact identity here does matter. It will have implications of like here, this is the alkoxide form, where we have the negatively charged one. And if we have the negatively charged one, we will also have the neutral one in some capacity. But if we just have the neutral one, then it is just an alcohol. Poor base, poor nucleophile. And so that will be important. Cool. Okay, let's talk regio and stereochemistry for E2. So I want you to take a second, look at this molecule. think to yourself and identify how many beta hydrogens do we have on this molecule. And once you have your answer, I want you to show me with fingers. 1, 2, 3, 4, 5. Give you all like 5 more seconds. Okay, hands. Okay, we've gotten consensus. I don't know if that is just looking around the room, but yes, there are 5. Let's see where they are. 1, 2, 3 on this side, and then 2 right here. So now our kind of issue is we have lots of choices for which beta hydrogens we can choose to deprotonate. And so we need some kind of ranking system that's going to tell us which of these isomers we are going to get more of. Because oftentimes with these reactions, you're going to get multiple products, but we are typically asking for the major product, the one that has the greatest percent. So we use Zaitsev's rule. Zaitsev said, and he just like did his like research in his lab and noticed, hey, when there are fewer hydrogens on an alkene, it's more stable. So another way of saying that is more substituted alkenes are more stable. So more like carbon things on an alkene, fewer hydrogens. So if we look at the isomers up here, we have 2 big camps. So one is, if our alkene's on the end of a molecule, we say it's a terminal alkene because it terminates the molecule. And then if it's not on the end, it's internal. So which of these, between terminal or internal, which is going to have more hydrogens on the alkene? Internal or terminal, which is going to have more hydrogens? The terminal. Because you know if it's on the end, then it's going to have at least 2, and this one has a 3rd. Versus if we look at these internal ones, these only have 2 hydrogens on the alkene. So, which of these is going to be more stable, the internal or the terminal? The internal, and that's just based on Zaitsev's rule. So the 2 hydrogens are here, the 3 hydrogens are here. So we only get, I think, 25% of this terminal alkene. These are not numbers for you to memorize. This is just kind of an example so you see the trend. Okay, and then among the internal alkenes, which do you think we're going to get more of if we can form both the trans and the cis? Which is more stable? The trans. So the trans, we are putting our bigger groups opposite each other, whereas the cis one over here, we are going to have some steric interference between this methyl and this ethyl. And so because of that, we expect to get more trans than cis. And the percentages are 41% trans and then 14% cis. So that's 55% internal total. And this would be with a good base like NaOET, I believe. So what do you notice about these percents? It's not 100. So again, this is the idea that a lot of different reactions can happen to the same molecules. And so even though we didn't list it here, SN2 probably can happen and is probably some of that remaining 100%. Cool. So our kind of takeaways from this is when we have options for where to form our alkene, more substitute is favored, and that's Zaitsev's rule, and then trans is favored over cis. So those are kind of our 2 things that hold true. But just like all of organic chemistry, nothing is holy. There are no hard rules. We can mess with this a little bit. So let's talk about messing with it. So if we wanted actually to make our terminal alkene, and we didn't want to get our Zaitsev product, our internal one, we could use COP2, tert butoxide. And what it's going to do is it's only going to get, or it's going to get a majority of this terminal product, terminal alkene. The reason for this, it has to do with accessibility. So when you form the terminal alkene, you are going to be attacking this carbon here, which is on the end of the molecule. And when you are a bulky base, like tert butoxide, those are just going to be more accessible. And so it's going to form its alkene terminal. rather than these over here. That's going to be harder to reach because you have more carbon groups around it. We call this terminal version the Hoffman product. And I could be getting this wrong. I might just be spreading lies. But I think Serenia studied under Hoffman. Like, I know she has some, like, chemistry pedigree of, like, she has studied with a professor who, like, has named reactions. But yeah, I think she studied with Hoffman. This could be a lie. So next time you see her, ask her. But yes, that's kind of messing with the stereochemistry if we want to get the terminal. This will be important for synthesis, where we want to control these things. Cool. So for the practice, I have not given you an easy thing, I've given you a slightly hard thing. This is something that most other OChem classes does not test. And it's something that we like to test because it combines a lot of topics that we study. And this is going to be the subject of like 2, if not 3 of the challenge problems. So I wanted to get some practice doing it here. Doing E2 on a ring. So when you do E2 on a ring, you must draw a chair structure to help rationalize what's happening with you, or with the reaction for yourself. Oh, that's a janky chair. Oh, that's a really janky, I'm so sorry. We're gonna go with it for a minute. So we can draw a version of this bromine where the bromine's axial and a version where it's equatorial. But we know that we have to have that anti-periplanar geometry, right? So if I look at the beta hydrogen positions on these molecules, for this right chair, are any of those hydrogens at the beta position anti-periplanar to this bromine that's equatorial? No. It's kind of hard to see. Like, it would be easier to build it and kind of visually see it. But none of them are going to be that exact anti-geometry that we want. Whereas over here, that position and that position are going to be anti-periplanar to the bromine. So to do E2 on a ring, your big takeaway is E2 on a ring, your leaving group needs to be axial. So what this means for the practice is I want you to draw the 2 chairs associated with this molecule, and then pick which one is going to be able to react E2, and then try to determine what the product's going to be.
So in order to be E2, it has to be
Anti-periplanar.
So your unit has to be
Axial.
axial.
Axial. It could point down and be axial, but so if you are doing an E2 with a beta hydrogen on the ring, yes. There's one kind of weird exception where I'm being very careful with my wording because it is a challenge problem where something weird happens that you'll kind of reason and think through. But So did you get these chairs? As if it was just kind of a exam one problem. Draw the two chairs. In yours, you could have put them on slightly different positions, but one of them should have both the BR and methyl axial. One should have both the BR and methyl equatorial. So, here, just like what we said earlier, for this bromine, when it's equatorial, none of these are going to be anti-periplanar. So just tracing them out, these, if I did a Newman projection here, that would be like having the BR like this and the hydrogen in the back up top. That's not anti. Similarly down here, that would not be anti either. And it's kind of like one goes diagonal down, one goes diagonal up. Here, like these are both going up, so that it's not up and down anti. So nothing works here. Over here, among our 3 beta hydrogens, the only one that's going to be anti is this. So our only option here is this one where the hydrogen is axial down. So you need both the hydrogen and the leaving group to be axial to do E2 with a member of a ring. So if we know that we're going to be deturning there, that means that we're essentially making our double bond kind of in this position for our regiochemistry. So our final product that we can just draw, and we don't have to draw it as a chair, would be this. And that would be our major product, even though it's not the more substituted one. Like, you could on paper draw this, but this is impossible based on geometry, even though this is one that looks more stable. It's tricky. E2 on the ring. I did not give y'all like an easy practice to do. Like SN2, I gave you easy practice. For this, which of these two chair conformations, the left one or the right, which one's more stable? The right one. More stable. And it's because they're equatorial, right? It's more stable, but it is not E2 reactive. Whereas the left one is less stable, but is E2 reactive. And remember, these two conformations, the molecule is like wiggling. It's kind of going back and forth, it's doing chair flips. And so even though it's going to spend more time in this more stable position, it will go to this less stable position, which can do E2 reactions. And so you will be able to access this. Now, can I ask a critical thinking question? Or are we in a space where we could do a critical thinking question? We'll see. What if I made this a tert-butyl instead of a methyl? Then could this still do E2? What do we know about tert-butyls on rings? So, y'all said the exact opposite. It's related to stability. E2, or a tert-butyl group has to be equatorial. It cannot be axial. And maybe that's what you said and I just misheard it. Sorry, that is what you said. So, if a tert-butyl group has to be equatorial, is this thing going to be doing ring flips? No. It has to be locked in this position. If it's in this conformation here, can it do E2? No, it can't, because it doesn't have any anti-periplanar hydrogens. None of these would work to be anti-periplanar. So, again, there are lots of ways that we can ask kind of conceptual questions related to this, and so I wanted it to be on your radar. Any questions on E2 before we go to the last family? Gonna try, but I've also been trying for the others and have not. It was a thing where I was like gonna get up this morning and do some work. I was gonna wake up at like 4:30 or 5. Woke up at 6. Was late to my first section. So we're trying. We're trying. Last family, SN1E1. So the big difference between SN1E1 and SN2E2 is that SN1E1 proceeds through a mechanism that involves a carbocation. So What happens, imagine you're a halogen. Imagine you're in a bond relationship here with a carbon. And time goes by, and then it's like, hey, this is not working for me anymore. I need to just leave. And, sometimes that leaving can be a positive thing. And when the halogen leaves, it can create a carbocation here. So once we have a carbocation, here, two options can occur. Either our other molecule can act as a nucleophile and just go and attack it, and we get a substitution product, which we call the SN1 product. Or the other molecule can act as a base, deprotonate at the beta position, fold in, make an alkene. This elimination we would call the E1 product. So this is kind of the bugaboo thing of both of these. Whenever you can have one of them, you can have the other one. They are always going to be happening together. You're always going to get a mixture for the most part. And that's going to be something that we have to control for in a bit. Very quickly, the reason why we have the 1 here is because this is a first order rate law with a reaction. The slow step by far is the leaving group just spontaneously leaving, because that just takes a long time. The molecule is not going to want to go into this high energy state. And so, because that's the slow step, the rate of this reaction only depends on the concentration of this molecule, this one molecule, so first order. But again, the confusing thing, how many steps is this reaction? 2. SN1 and E1 are 2 steps. SN2 is 1 step. I hate it. So sorry. So, because you have this slow step for both of them, the major factor for predicting whether or not SN1 and E1 is going to happen is how stable is our carbocation that we form. So we have 2 ways of stabilizing the carbocation. The first one was introduced yesterday in lecture for the first time, and it's called hyperconjugation. And I'm going to give you my very layperson metaphor of hyperconjugation. So imagine there's a house, and the house is going through some disaster. And the disaster in this case is a carbocation and needs electrons. But in a metaphor, it could be like a fire, a flood, a famine, something. Hyperconjugation is going to be when this neighboring sigma bond kind of leans over to the carbocation and it's kind of like, there. Sorry you're going through a rough time. I'm just going to lean my electrons a little bit towards you, not giving them away, just leaning them. And that lean and the little pat on the back, that's kind of minor stabilization. So at the end of the day, she still has a positive charge, but some of these electrons are a bit closer to it that help stabilize. That's hyperconjugation. And if we compare it to resonance is like, oh, you have a positive charge? I have a positive charge. I will take this on with you. I'm your ride or die. We're going to spread out this charge, delocalize it across everyone, and that's really stabilizing. That's much more stabilizing than hyperconjugation. But hyperconjugation, the nice thing about it is these small stabilizing interactions where it kind of leans over can stack. Like here, we have 3 of these interactions that are all happening together. And as you go from a primary to secondary to tertiary alkyl halide, you get more and more of these stabilizing interactions of hyperconjugation. And so what we see is that secondary and tertiary carbocations are fairly stable because they have either 6 or 9 of these stabilizing interactions. Now I know I explained this in a not very chemistry way, like a very, again, kind of plain English way. Do you have questions on hyperconjugation and what she is and how she is stabilizing? Yeah. Yeah, so it is a donation for MO theory. We can think about it is a donation from this sigma orbital into the 2bc, and there is some overlap, and it lowers the energy just like a bonding interaction. But it is much weaker than forming an actual bond. To really explain it, it requires physical chemistry, and it's a bit much. But I think about hyperconjugation as the exact opposite of induction. Induction was kind of pulling electrons away from something. This is kind of leaning electrons towards it. Thank you so much for bringing that up. The other thing is, you might remember on PSET 2, on the answer keys, we just said at some point that alkyl groups were electron donating. This is the why. So we wanted to kind of plant the seed of that idea early on, but we didn't really explain it. And the explanation here is this is going to donate electrons a little bit via hyperconjugation, and it's going to help stabilize the partial positive here. So, you've seen it a little bit before.
Is it opposite of alpha groups or is it
So carbon-carbon bonds can also engage in hyperconjugation, but it's just weaker. We won't ask you to differentiate between that, so it's really just, is the carbocation primary, secondary, or tertiary? And that will give you a good read on how much hyperconjugation is going on. Yeah. Good question. And so they're more stable. Yeah. Now, so this is the first way that we can stabilize a carbocation. The second way is resonance, which we already said is way better. So tertiary, which was at the top of the stability over here, is the bottom of the stability here. And I might even do like a double. Like this is even less than just the basic resonance here. So this position here that's like right next to an alkene, we call the allyl position, A-L-L-Y-L. And this would be an allylic carbocation. She has resonance. So she has a resonance structure that looks like this. We are fully spreading that positive charge out across 3 atoms, so it's just more stable. Similarly, the carbon that's right next to a benzene ring is called the benzylic carbon. And the benzylic carbocation has a lot of resonance. It has resonance coming from all of this ring, so you're spreading the positive charge out over like 7 atoms. Same with adjacent to a atom with a lone pair. So, in the wild, what this will look like is you will see something that looks like this, where it's an alkyl halide, where this looks like it's a secondary alkyl halide, right? But its carbocation is way more stable than secondary because it's this benzylic one that has resonance. So that's the thing to kind of keep the eye out for, of is there any resonance nearby that could stabilize a carbocation. Okay, I'm going to try to wrap this up fairly quickly and then get to the practice because that's going to be the more engaging part. We have to think about stereochemistry a little bit. Be ready. So earlier, stereochemistry, when we talked about SN2, the first thing that you should think is, thank you so much, thank you so much. But for when we have SN1, we're doing a different mechanism here. We have this carbocation that has an empty p orbital. This p orbital has a lobe above the plane of the other atoms and below, and our nucleophile could either attack from the top or the bottom. If it attacks from the top, that could make the S enantiomer of the molecule. If it attacks from the bottom, it could make the R enantiomer. And so the big thing for SN1 is you're going to get a mix of R and S for your addition, whereas SN2, you're only going to get one product. I gave an example here of like when that's not going to be a 50-50 mixture, but we don't really ask about this, so it's not that important, but you can read it if you want. For E1, it just follows our like Zaitsev rule of like internal trans alkene are favored. So it's kind of just like E2 for like which one's formed. The big thing I hinted at earlier is like when you have SN1 as a possibility, you are also going to have some E1 happening. Like they always happen together. So we need to kind of make some ground rules for how to control which one we want as our major product. And our default tiebreaker is SN1 predominates over E1 simply because it's faster. It has to do with the fact that like this is like a one arrow mechanism of these two things just have to bump into each other. Whereas this, there is a little bit more alignment of the p orbital and the sigma bond, and it's like 2 arrows, and so it's slower. Like that's the rough idea. So with everything else equal, if you're in SN1 E1 land, SN1 wins as the major product. There's still probably some E1 formed, but again, we care a lot more about what is the major product produced. Now, we can mess with this by changing the temperature. So if we increase the temperature, we could get more E1. Again, we don't really test temperature, so don't worry too much about it. We do, however, need some way of getting only E1 because we were trying to do synthesis and like it's going to be very helpful for us. And our way of getting only E1 as the product is by using an alcohol, a secondary or tertiary alcohol, with concentrated H2SO4. And so because of this conc, we might say we conc it to get E1. Just a little memory thing. So the way this works is this is sulfuric acid. She's a strong acid. So we are going to protonate the alcohol and makes it OH2+. Is OH2 plus a good leaving group?
Yes.
Yeah. So it will leave on its own, make a carbocation. And then at this point in the mechanism, the only things that we have around are the water that we just kicked off, the conjugate base of sulfuric acid, and then more sulfuric acid. So if the water went and tried to do an SN1, it would just go backwards. It would go to this step, and so that doesn't really affect anything. Like, we're not going to get a different product out. But this thing over here, this bisulfate, it fully will not act as a nucleophile attacking the empty p orbital. It has to do with the fact that this thing has a lot of resonance, and also sulfur has a bigger atomic radius, and it kind of is spreading out the charge. But this thing just fully won't attack the empty p orbital. And so the only thing that it can do is it can act as a weak conjugate base and deprotonate here at the beta position and make an alkene. So this is our way of, the only way really, to get only E1 for our class. I just spoke a lot of things at you. Let me give you a short exercise. So I want you to put on your investigative journalism hats. I've given you a reaction here, and I want you to determine whether or not this reaction, which is some sort of substitution, I want you to try to determine, is it SN1 or SN2 that happened? And then try to think of about 3 reasons to justify your answer. So take like 90 seconds. So, can you, with your hand, either put up a 1 if you think it's SN1, or 2 if you think it's SN2? Okay. Of the hands I'm seeing mostly 1, and that is correct. So, can someone give a reason why they think that this is SN1? Sergio. Yeah, so you see over here, it's wedge, and here in the product, it's in the same spot, and it's wedge. So we didn't invert the stereochemistry for this. But actually, have y'all seen this symbol before? The plus minus with a dash between it, or a slash between it. So this is a shorthand notation to say that both enantiomers were formed. And this notation comes from, remember you talked about plane polarized light, and like it rotates it in the positive direction for one enantiomer or negative for the other? That's kind of where this comes from. And so it's just a shortcut for us, instead of writing out both of these products of here it's on a dash. And this is a notation that you can use, and you will be allowed to use on exams and everything, where if you write this, it means you have whatever you drew and you have its enantiomer in a mixture. So we got a mixture of products. That's a dead giveaway for SN1. What's another reason for why SN1? Yeah, so if we think about that carbocation that would form, this is truly the molecule I drew right here, where we would have a carbocation at that benzylic position, and that's going to be stabilized by a bunch of resonance. Boop. So, second Y reason is very stable carbocation. Any other reasons? Those are kind of the big 2 ones. Another one that like I heard from some students is like this is secondary. So because it's secondary and we have a big phenyl group, it's probably not going to be a good candidate for SN2 because of sterics. SN2 bulky is bad for SN2. And then also, like, this is not a very strong nucleophile because it's an alcohol. So there are lots of ways that we can think about it. But this kind of detective work of was this SN1 or SN2, that's going to be a bigger theme of lecture 7 tomorrow, because a lot of the reactions that you are going to learn are going to build on SN1 and SN2. Cool. Okay. Any questions on this last big family? I know that this one was tough, and I see many people fading in energy. I got some nods about the fading in energy. Yeah.
I was thinking more for yesterday as like accident or not happens with one. So like it's not that.
It is when you form the carbocation, SN1 or E1 could happen.
I think she was like S1 happens like that's why I was
Yeah, no. Okay, so let's put it all together. So, again, the challenge with this lecture, and I'll show you what a page of your exam is going to look like. It's going to look like this, where we are going to give you like 5 box problems, and this is from the PACS exam, so you don't need to take a picture of it. But we are going to ask you what mechanism happened, SN1, SN2, E1, E2, and to draw the product. And so this is a skill that we really want you to get good at. So,
Can some of those have like 2?
not if we're asking on an exam. Like, most of them are going to have multiple products, but we asked for that specific one, what is the major product? What is the one that's going to have the greatest, like, concentration in your products? So, all of these reagents and starting materials look very similar. We're doing a bunch of stuff with alkyl halides, essentially. And so we need to be able to determine which of these is going to actually take place, which one of these mechanisms. And so to do that, we're going to go through each one of these families, SN2, E2, and SN1, E1, and we're going to rank how compatible our reagents are with this mechanism as either good, fair, or poor, GFP. And I will say at this point, I've probably seen like 15 different colleges, how they teach it, from like tutoring, and I've seen maybe 7 or 8 OChem textbooks of how they teach it. This is, I don't want to call it my favorite system. This is the system that I hate the least for teaching this, because they're all really like convoluted and really complicated, and this at least kind of gamifies it, which is nicer. But it's not perfect. None of the systems are perfect. This is the one that I feel like works the best. So, for ranking favorability of a reaction for SN2, the big thing that we pay attention to is sterics. So if it's methyl or primary alkyl halide, it's going to be good, secondary fair, tertiary it's poor. The other thing that's going to make it poor for SN2 is if we have a bulky base like our tert butoxide. So again, she keeps coming back, and she will. Then for E2, the big thing that's going to determine good, fair, poor is our base strength. So these were the ones that we had highlighted green, orange, or yellow in the chart on the other page. Then finally, for SN1, E1, carbocation stability. So it's going to be good if it's tertiary or better. And that means resonance. So if you have resonance, you're already going to be good for SN1, E1. Fair for secondary, poor if it's methyl or primary. We have 2 kind of like quality assurance checks. Yeah? Then it's up in the good, because resonance trumps everything else. So we have to do 2 quality assurance checks on this. This is not sufficient alone. So the one is just a vibe check on the nucleophile. So if you're doing this, it's really easy to forget about this thing. And so you just have to check yourself, do I have a bulky nucleophile? And if I do, I bump it down to poor. If you have some other thing that's not as good of a nucleophile, it's probably going to have an effect, but it might go from like fair to fair minus. It's not going to automatically bump it down to poor. The other one is an E2 reality check. Do you have a beta hydrogen? Can it be anti-baryplanar? And then finally we have tiebreakers. So the tiebreakers is just the speed of the reactions. So like let's say you were tied for SN2 and E2, SN2 would predominate because SN2 is faster. Similarly, like here, if you were tied between E2 and SN1, E1, if they were both good, E2 would win because it's faster. And so this is the order of the speed of the reactions. Okay, so I'm going to do the first like 3 with y'all, and then I'm going to let y'all work for like 10 or 15 minutes and like talk to each other and then we'll go over some at the very end. But let's kind of talk through this and kind of how to do this process. So I'd start off with ranking SN2 favorability. So I look at the alkyl halide. Is it primary, secondary, or tertiary? Primary. So is it good, fair, or poor for SN2? Good. Then I do my nucleophile vibe check. I have Naomi or methoxide. Is that a good nucleophile? Yeah, it has a negative charge. Great. So good. Then E2, I look at the base strength. So this is OME minus, which is like an OR minus. Is that a good, fair, or poor base? Good, yeah. So we say OH minus or stronger is a good base, and OR minus is just like OH minus. They're around the same level. So good. And then SN1E1, we look at the alkyl halide. It's primary. So is it good, fair, or poor? Poor. So then we have a tie between SN2 E2. Who wins? SN2. I would encourage you not to, because you'll get to where you can do this process in like 30 seconds or less, and it's worth doing it just to see if there are other options. Yeah. So over here, I would just draw the product where I've done the substitution. And it's not stereocenter, so we don't even have to worry about inversion of stereochemistry. On to the next one. I start off with SN2. So is it primary, secondary, or tertiary? Primary. So it's good for SN2. Then I do a vibe check of the nucleophile. Is this a good nucleophile? No, this is our tert butoxide. So it's a bulky nucleophile. That's going to make this poor for SN2. So again, it's one of those pitfalls where you have to be kind of doing these little checks. Okay, E2, is tert butoxide a good base? Yes, that's its whole deal. If we go back to where we introduced it, it is a poor nucleophile but strong base, and it's one of very few molecules in the class that will be like this. So it's going to be a good candidate for E2. Then it's primary, so is it good, fair, or poor for SN1E1? Poor. We have a clear winner here of the E2, so we just draw the elimination product. And I'm going to do one last one. So with this third example, is it primary, secondary, or tertiary? It looks a little weird, but we have 3 methyls and a chlorine on a carbon, so it's tertiary. So is it good, fair, or poor for SN2? Poor. E2, we look at base strength. We have OET minus, good, fair, or poor? Good, because it's just OR minus. And finally, SN1E1, we have tertiary. So are we good, fair, or poor? Good. Okay, we have a tie between E2 and SN1E1. Who wins? E2, just because it's faster. So our product is our elimination product. And if you drew it like this, that is the exact same molecule. Same if you drew it like this. They are just all rotations. So I want you to try this out. These are pages 5, 6, and 7 of the problem set. 5 and 6 are pretty straightforward of these kind of quick practice. 7, each question is trying to trick you. So just be warned. Yeah, this is the pizza. Yeah. So let's take like, I don't know, 10 minutes-ish.